In this lesson, we are going to learn to find power series that represent specific functions. So first we're going to find a power series representation of f of x equals 1 over 1 minus x, centered at 0. And we're going to figure out which values of x gives us convergence of this series. So what a lot of this is going to rely on in this lesson is the sum of a geometric series. So recall that the sum of a series from 0 to infinity of a r to the n, this is equal to a over 1 minus r as long as the absolute value of r is less than 1. So what we're going to do with this lesson is actually use this backwards. So here's how. I have my function f of x. It's equal to 1 over 1 minus x. Now, look at how that's similar to this a over 1 minus r. The a is the number in the numerator. A is equal to 1, and r is equal to x. So this expression, going backwards, can be written back into its sum form from 0 to infinity, a times r to the n, so 1 times x to the n. Or my function f of x is equal to a sum from 0 to infinity, x to the n. So as in, this tells us that 1 over 1 minus x is equal to, well, 1 plus x squared plus x to the third, up to x to the n, etc. Now, that is only true if the absolute value of x is less than 1, or x is in between -1 and 1. But this is the power series representation of 1 over 1 minus x centered at x equals, or centered at, I guess we should say, c equals 0. And it's only valid between -1 and 1. So next, let's find a series for the same function, but this time it's centered at -1. So f of x is 1 over 1 minus x. If we want to be centered at -1, we need to have this say x plus 1. So I've actually taken away 1 in the denominator, which means to compensate I have to actually add 1. You've seen that trick before when you completed the square. So remember that the sum of a geometric series from n equals 0 to infinity, a r to the n is a over 1 minus r. So first of all, this is 1 over 2 minus x plus 1. We need to manipulate this expression so that that 2 is a 1, and here's how you do it. Factor out the 2, so it becomes 1 minus x plus 1 over 2, or 1/2 over 1 minus x plus 1 over 2. And now in this case we have a is equal to 1/2 and r is equal to x plus 1 all over 2. So this can be written as the sum from n equals 0 to infinity, 1/2 x plus 1 over 2 all to the nth, which is the same thing as the sum from n equals 0 to infinity, x plus 1 to the n over 2 to the n plus 1. And that's because we have a 2 to the n in the denominator multiplied by another 2 is 2 to the n plus 1 power. Now this one will converge if the absolute value of x plus 1 over 2 is less than 1, which implies that x plus 1 absolute value is less than 2, or -2 is less than x, which is less plus 1, which is less than 2, which implies that -3 is less than x, which is less than 1. So that particular expansion is good for all x's between -3 and 1. So everything today is going to rely on that manipulation to make this into the form of a geometric series. So it's best to keep in your mind that the sum from n equals 0 to infinity a r to the n is a over 1 minus r. So to make your function in the form 1 minus something in the denominator. So first of all, let's factor out that 4. So we'll have 4 times 1 plus x over 4. Alright, so that's the same thing as 2 over 1 minus negative x over 4. And now using the fact that a is equal to 2 and taking r equal to negative x over 4, this is the same thing as the sum from n equals 0 to infinity to negative x over 4 to the n, which is the same thing as the sum from n equals 0 to infinity, negative 1 to the n times 2x to the n over 4 to the n. Now, this is a little bit tricky, but you can actually simplify this a little bit further. This is a good enough answer in general, but just in case something like WebAssign requires you to make it a little bit different and combine anything that can be combined, notice that 4 to the n, so 4 to the n is the same thing as 2 squared to the n, which is 2 to the 2n. And then if I had 2 over 2 to the 2n, that would be the same thing as this 2 would be the first, that would be 2 to the 1 minus 2n, or factoring out a negative, 2 to the negative 2n minus 1. So this could also be written as negative 1 to the n, x to the n over 2 to the 2n minus 1. Just in case that happens. It's not necessarily something I'd want you to do, but it's those kind of tricky manipulations can occur. So find a power series for this function, but this time centered at 1. So we have to have an x minus 1 in our r's expression. So we'll have x minus 1. I've actually taken away 1, so I have to add 1. So 1 plus x minus 1. Now that's the same thing as 2 over 1 minus negative x minus 1, which then, using the fact that the sum from n equals 0 to infinity a r to the n is a over 1 minus r. Now we take a equal to 2, so this is a sum from n equals 0 to infinity to negative x minus 1 to the nth, or sum from n equals 0 to infinity to negative 1 to the n, x minus 1 to the n. And this will converge so long as the absolute value of x minus 1 is less than 1, which means x minus 1 is between negative 1 and 1, or x is between 0 and 2. So that's the interval of convergence. Or you could express that also as 0 to 2. So find power series representations of these functions, both centered at 0. So first of all, for this one, I must factor out that 2. And then I can make it into 1/2 over 1 minus negative x over 2, which then becomes a sum from 0 to infinity, 1/2 multiplied by negative x over 2 to the nth, which is the same thing as the sum from n equals 0 to infinity, negative 1 to the n, x to the n, over 2 to the n plus 1. Alright, so there's an expression for f of x. Now let's also find the interval of convergence. I didn't say to in the directions, but I'm pretty sure you have to in your homework. So the interval of convergence, we must have x over 2 being less than 1, So x is absolute valued less than 2. So my interval of convergence is from -2 to 2. And because this manipulation was based on a geometric series, at the endpoints we're not going to ever have convergence when you straight up use the geometric series formula. So your interval of convergence is from -2 to 2, non-inclusive. Now the thing to notice with this particular example is that this is x cubed multiplied by 1 over 2 plus x. So what I can do is take the series I found for 1 over 2 plus x in the previous example, which was the sum from n equals 0 to infinity, -1 to the n, x to the n, over 2 to the n plus first, and I can multiply the x cubed through, which gives me a sum from n equals 0 to infinity, -1 to the n, x to the n plus 3. And it's because x to the n times x to the third, the exponents add, all over 2 to the n plus first. And the interval of convergence here has not changed. We'll still have the interval of convergence is -2 to 2. Now suppose we have two convergent power series. Here's some operations that you can do with them. You can put a constant inside of the function, and that kx can replace this x to the n, and you'll have kx to the n giving you k to the n, x to the n, as you see here. You can insert something to the nth power, so you'd have x to the capital N to the lowercase n, those powers multiply, giving you x to the capital N lowercase n. And you can also add two series together. But just be aware that these operations can change the interval of convergence. So for example, in addition, the interval of convergence for the sum or difference is the intersection of the intervals of convergence. So supposing that f had an interval from -1 to 1, and g's was larger, say it was -3 to 3, the sum will only converge where both components converge, and both components converge where the two intervals intersect, or overlap, which is -1 to 1. So let's find the interval of convergence for this sum. So first of all, let's discuss how this whole factoring addition thing came about. So I have a sum from n equals 0 to infinity, x to the n, plus another sum from n equals 0 to infinity, x to the n over 2 to the n, which I then expressed as one sum, x to the n plus x to the n over 2 to the n, and then the x to the n was factored out. So that gives us 1 plus 1 over 2 to the n times x to the n, giving us this. And I think that's always going to be required, that you always factor out greatest common factors. Now let's find the interval of convergence. So for the first series, so for series 1, we have convergence if the absolute value of x is less than 1, which implies that my interval of convergence is -1 to 1. For the second series, I have convergence if the absolute value of x over 2 is less than 1, which implies that the absolute value of x is less than 2, which implies that x is in between -2 and 2. Now, looking at that on a number line, say we have -1 to 1, everything in there works. -2 to 2. Now these two series overlap between -1 to 1, so this series where we have added them together has interval of convergence -1 to 1. Find a power series representation of this function. Now, we don't have any formula for having sort of like an x squared and an x in the numerator, so the hint here is you're going to use partial fractions. So 3x minus 1 over x plus 1 x minus 1 is equal to a over x plus 1 plus b over x minus 1. Our job is to find a and b. So we'll have 3x plus 1 multiplying by x plus 1 and x minus 1, a times x minus 1 plus b times x plus 1. So 3x plus 1 is equal to x times a plus b, and then minus a plus b. So we have that a plus b has to equal 3. I should have missed a minus sign there. That would have screwed everything up. And I have that negative a plus b has to equal negative 1. I'm going to use elimination. I'm going to add these two equations together. That gives me 2b equals 2. So therefore b is 1. And if b is 1, it appears that a must equal 2. So now we know that 3x minus 1 over x squared minus 1 is equal to 1 over x minus 1 plus 2 over x plus 1. And we can find series for each of those individually and then add them together to get a series for the entire thing. So let's start with the 1 over x minus 1. That's the same thing as negative 1 over 1 minus x, which is equal to a sum from n equals 0 to infinity. Negative 1 is my a, and then just r is x, x to the n. This will converge as long as the absolute value of x is less than 1. So it has interval of convergence negative 1 to 1. Now 2 over 1 plus x is a little bit harder, but not ridiculous. 2 over 1 minus negative x. So that will equal a sum from n equals 0 to infinity. 2 times negative x to the n, which is the same thing as a sum from n equals 0 to infinity, 2 times negative 1 to the n, x to the n, and this also converges if the absolute value of negative x is less than 1, which is the same thing as x being between negative 1 and 1. Now 3x minus 1 over x squared minus 1 will be given by the sum of these two added together. And let's just take out the greatest common factor right away. So the GCF will be x to the n. From the first sum, I have a negative 1 left. From the second sum, I have 2 times negative 1 to the n left, and then all multiplied by x to the n. And the interval of convergence of this series is the intersection of these two intervals, which happen to be the exact same thing. So this has interval of convergence negative 1 to 1. Now, the final technique we're going to learn is how to use integration and differentiation to obtain a power series. So let's do a few examples. So f of x is 1 over 1 minus x squared, and we want to express this as a power series using differentiation. So what you notice is that if you integrate 1 over 1 minus x squared, that's the integral of 1 minus x to the negative 2. That's, other than the plus c, 1 minus x to the negative first divided by negative 1 and then multiplied by another negative 1. So that's 1 over 1 minus x. And what that means is if I differentiate 1 over 1 minus x, I end up with 1 over 1 minus x, the quantity squared. What this means is that I can find a power series for 1 over x, and if I differentiate it, I'll get a power series for the thing that I want. So first notice that the power series for 1 over 1 minus x is just the simple one you've been discussing from pretty early on. 0 to infinity is just x to the n. That's it. So that tells us that 1 over 1 minus x, the quantity squared, will equal the derivative of this series, which is equal to a sum from n equals 1 to infinity, n x to the n minus 1. And technically the radius of convergence will not change, so we still have a radius of convergence, r equals 1, like in the previous example. It is possible, which means the interval of convergence, at least preliminarily, is between negative 1 and 1. Now you could have convergence at the endpoints, In this case, neither of them work, so this is your interval of convergence. But that's the one thing to be careful about, is that if you use integration or differentiation, the interval of convergence may change at the endpoints. So in the previous example we used differentiation. Next let's use integration. So here you have ln of 1 minus x is what you'd like to find a power series representation for. So notice that the derivative of ln of 1 minus x is 1 over 1 minus x multiplied by negative 1, so negative 1 over 1 minus x. And that implies that the integral of negative 1 over 1 minus x is equal to ln of 1 minus x. So if I find a series for negative 1 over 1 minus x, and then anti-differentiate it, I will have a series for ln x. So negative 1 over 1 minus x will equal a sum from n equals 0 to infinity negative 1 x to the n. Then ln x, ln of 1 minus x will equal the integral of this. So the integral of this series, sum from n equals 0 to infinity negative 1 x to the n, which is a sum from n equals 0 to infinity negative 1 x to the n plus 1 over n plus 1. And the original series, this had interval of convergence negative 1 to 1, non-inclusive. What we have to do for this final series is check the endpoints. So at x equals 1, we're going to get the sum from n equals 0 to infinity negative 1 over n plus 1. That diverges. You can use a comparison test, limit comparison test, or comparison test with the harmonic series. However, if x equals negative 1, we have the sum from n equals 0 to infinity negative 1 multiplied by negative 1 to the n plus first, all over n plus 1, and this is going to be an alternating series. So this will converge by the AST. So for the series for ln of 1 minus x, the interval of convergence for this includes negative 1, but does not include 1. And then let's do one more example with integration. Let's talk about arctan of x. So first notice that g prime of x is equal to 1 over 1 plus x squared. So if I can find an expression, a power series for 1 over 1 plus x squared, if I integrate 1 over 1 plus x squared, I get back arctan. Alright, so now notice that 1 over 1 plus x squared is the same thing as 1 over 1 minus negative x squared. So taking a equal to 1 and r equal to negative x squared, we'll have a sum from n equals 0 to infinity 1 times negative x squared to the n, which is the same thing as the sum from n equals 0 to infinity negative 1 to the n, x to the 2n. So that's for arctan, and it converges so long as negative x squared absolute value is less than 1, which means x squared is less than 1, or x is in between 1 and negative 1. At the endpoints, no convergence. So then to find arctan, arctan's power series centered at 0, we will integrate this. And so that gives us the sum from n equals 0 to infinity negative 1 to the n, x to the 2n plus 1, all over 2n plus 1. So there's an expression, or there is an expression for power series for arctan centered at 0. The final thing we need to do here is check for convergence and divergence at the endpoints of that interval. So if we plug in x equals negative 1, I get the sum from n equals 0 to infinity negative 1 to the n, negative 1 to the 2n plus 1 over 2n plus 1. And we need to see if these terms alternate. So suppose when you plug in 0, negative 1 to the 0 is positive, negative 1 to the 1 is negative, so first term negative. When you plug in 1, the first term is negative, the second term is negative, resulting in a positive. When you plug in 2, positive, negative. So this appears to be alternating, so this does converge at x equals negative 1. So by the AST, this will converge. And at x equals 1, even easier, we get the sum from n equals 0 to infinity. Negative 1 to the n, 1 to the 2n plus 1 is 1 no matter what. So over 2n plus 1, and that is obviously an AST, so this also converges by the AST, giving us an interval of convergence for arctan that's negative 1 to 1.